Alright, here we go with the FRQs for sample test number 2 with AP Calculus AB. So we're going to be doing numbers 1 through 3. Remember, the current exams, the calculator portion is actually numbers just 1 and 2, but right now these are older type practice tests, so that's why they have 1 through 3 all using calculator. Let's go ahead and start with this piece. We already have a graph here, a times this, and it says that a is between 0 and 1. That's going to be important for our understanding of what the graph looks like. And g of x equals this, and it's asking us to find the area of R in terms of a, when the area is in the first quadrant bounded by these two graphs. Well, it really depends on what a equals for us to find an exact value. So this is just asking us to start out with in general terms of a. So let's go ahead and work that out. If we know that a is between 0 and 1, anytime you multiply by a number between 0 and 1, it's going to make something smaller. Why? That's a fraction. That's like multiplying something by 1/2. Now it becomes half the size. If you're multiplying something by a number bigger than 1, that's going to give you something bigger than the original value. So if I multiply something by 2, it makes it bigger. So it's going to be smaller. So let's use that information as we try to graph these. I'm going to go ahead and I can use my calculator just to prove to you what these graphs actually look like. So let's start out with the first one. It says 36 minus x squared. Now I know the maximum of that, I'm only in the first quadrant, but the maximum, the y-intercept is going to be at 36. So my window should go pretty high here. Let's make it go, we're going to start at 0, first quadrant. We'll go out to 10, that's fine. But for the y values, I'm going to go from 0 all the way up to 40. So let's see what that would look like. So we have this curve. And just so you understand, this y-axis, it would actually be much taller than that, but right now the y-axis is kind of compressed just because of our window. So this is our curve, and what would happen if we multiply this by a, it still hits the x-axis at the same point, but it's going to hit the y-axis at a lower point, at this point here. So let's see what would happen with that. That means that this function, g of x, that's going to be on top, and that really matters because we need to know which one's on top and which one's on bottom in order to find the area between them. Because the area of R, the area of some region, is always the integral from the left side to the right side, x equals left to x equals right of the top minus the bottom. Now, if we were to translate things into terms of x and into terms of y, that would actually flip-flop where we're doing top and bottom, left and right in here. But let's go ahead and translate it since this is in terms of x. We know g of x is on top, so the integral is going to be g of x, which is 36 minus x squared. And then the bottom, it's going to be the other function, which is a, some constant, times 36 minus x squared. So that's our top minus bottom. What is our range? Well, let's take a look back at our graph just to see what we're working with here. We go out to 1, 2, 3, 4, 5, 6 is how far we're going to hit here. And just to give you guys an example, let's say a was 0.5. Then if I were to type that in, it'd be 0.5 times, and really it's the same thing as y1, so I'm going to just reuse that. I'm going to go to vars, y-vars, and then click on function, and I want just the first function, so y1. That way I don't have to retype it. Let's see what would happen, and lo and behold, it's lower, it has the same x-intercept, but it goes there. Just to show you that it's still going to have similar properties no matter what a is, as long as it's between 0 and 1. Let's say it's 0.3. Now, it's going to go even lower down here. Essentially, it's going to go that fraction of the whole distance. So, as we're trying to interpret that region then, our x boundaries are from 0 to 6. This is going to be dx. Now I can actually simplify this a little bit because a is a constant. So this would actually factor. It would be a minus 1, or pardon me, it's not a minus 1. It's 1 minus a, because this is times 1, this one's times a. I can factor out the 36 minus x squared. Why would I want to do that? Because this piece here is a constant. So I can go ahead and pull that out. That means I'll have 1 minus a times the integral from 0 to 6 of 36 minus x squared dx, of course. That just makes things a little bit easier because I have less anti-differentiation to do, but let's go ahead and work it out. The antiderivative of 36 is 36x. The antiderivative of x squared is x cubed over 3. And again, I'm multiplying that by 1 minus a. And I'm going to evaluate that from 0 to 6. I notice that when I plug in 0 into each of these, it has an x term, so I don't really need to have that. So it's going to be minus 0 on the bottom. But if I plug in the 6, that is going to matter. Well, let's see what 6 times 36 is. That's the same thing as 6 cubed. So 6 times 36. Wait, I have a calculator. Why am I not using that? 6 times 36. 216. We've got to use our calculators when we have them, when it actually makes it. So this becomes 216 minus 216 over 3 times 1 minus a. So r is equal to this. Now, in fact, we could have just simplified this even, but without even having to multiply that out. We could just plug in the 6 and show that it was going to multiply, but we didn't have to actually simplify that. So that's part A. Let's look at part B. Part B says, find in terms of A the equation of line L tangent to the graph of F at the point 6, 0. Well, we know that F, given to us already, is A times 36 minus x squared. So what it's asking us to do is find the equation of the tangent line. Well, we know that we have 6 and 0 as our x and y, and we're trying to find a tangent line. Let's think about point-slope form. Probably one of the easiest forms to plug in the pieces to. We need to find x1, y1, and m. We already know x1 and y1. That's 0 and 6. Whoops, those are backwards. Let's do those backwards. This is 0 for y and 6 for x. So we just need to know what is m. Well, to figure out m, we got to take the derivative and evaluate it at that x point. So let's first start by taking the derivative. Remember, a is a constant, so that just stays the same. So we take the derivative of this inside. Derivative of 36 is 0 minus the derivative of x squared is 2x. So if I were to simplify that even more, it's negative 2ax. It's f prime of x. Well, f prime, this slope right here is going to be f prime of 6. We're going to evaluate it at 6. Why? Because that's our x value. So we want to know the slope when x equals 6. That's going to be negative 2 times a times 6. In other words, negative 12a. So my tangent line then is going to be y minus the y value, which is 0, equals m times x. Oh, well, we know what m is. What is the slope? The slope in this case is negative 12a times x minus 6. There we go. Let's look at C. C, it says determine the value of A such that the line L divides the region into two parts of equal areas. Show the analysis that leads to your conclusions. Well, let's give ourselves some reference here with the graph so we know what's going on. We know that we have an x-axis, we have a y-axis. This goes up to about 36. Actually, it goes up to exactly 36. And it hits down here at 6. And we know that we have a curve. Let's cheat and use our little curve sketching. And then we're going to have another curve that goes down below it. Let's say it's here. Well, if we want to divide this region into two parts with equal areas, show the analysis that leads to our conclusion. That means that we're going to have some line here in the middle let's take it back. We're going to have some line here in the middle, and this line is going to divide these two into equal pieces. Now, this is kind of weird because we don't know exactly how to find where that would be yet. We're going to get to that in the next part. But let's say that we just had a line here in the middle, and let's take this piece here. Click on that one just by itself. It wouldn't look like it, so let's go ahead and erase this curve. What I'm looking for is, what if I had this other curve way down here? We're trying to divide this in half. This looks a little bit more possible here. Alright, that means that this blue area that I'm about to shade in this would be the same as this red. The blue and the red would equal each other. Well, let's determine what those two areas would be. Well, assuming that the top, this blue line, would be equal to the g of x minus the L. So let's do that real quick. The blue, call that A. Region A is equal to the integral from 0 to 6 still of g of x minus L. And region B is equal to the integral from 0 to 6 of L minus f of x, because in B, L is on top and f of x is on bottom. So if I were to label these, this is my f, this is g, this is my line f. So we want to make those two equal to each other. So determine the value of A such that this line divides the region into two parts of equal areas. We've got to show our analysis. So we've got to find the value of A. Well, we know what this region equals in terms of A. We figured that out in part A, actually, down here. So this is the region. So we want to split that in half. That's actually a lot easier than we would think. So if we want to split this in half, we're going to divide it by 2. We're just going to multiply this whole thing by a half. So let's go ahead and take a picture of that. Paste it on this page. Probably up here near the top. Okay, so this is our original region. Then what you want to be thinking about is we want to split that in half. Well, if we just want to split this in half, let's just take the whole thing and multiply by 1/2. That's it. So half of the area equals the whole thing times a half. That wasn't too hard. And because our first answer was in terms of A, let's go ahead and go on to part D. Oh, that was it. That was too easy. Too easy. Alright, next. The temperature T of x in degrees Fahrenheit in a small office building without air conditioning, that would be sucky, is given by T of x is 73 minus 14 cosine and a big old function where x is time elapsed since midnight from 0 to 24, so that must be in terms of hours. To cool a building, the air conditioning is turned on when the temperature first reaches the desired temperature and left on until the office closes at 6 p.m. That is when x equals 18, because that's the 18th hour, if you weren't catching on to that. So the air conditioning is turned on, and when the temperature first reaches the desired temperature, and left on until the office closes at 6 p.m. The cost per day, blah, 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 is this right here. This is our cost function. Estimate to the nearest half hour at what time the temperature will reach 70 degrees Fahrenheit. So we're trying to ask ourselves, when does this equal 70? Well, that's easy enough. Let's use our graphing calculator. So we have a big fancy function here. We go to y equals. We're going to clear out these functions and start some new ones. Our new function is 73 minus 14. We're going to multiply that by the cosine of, now inside here we got a numerator and denominator. In the numerator we have pi times x minus 3.4. Oops, not 3 minus, x minus 3.4. Divided by 12. We're taking the cosine of that. So that should be enough parentheses. Let's see if that works for us. Okay, now I'm graphing it, and I know that my graph is way off, so I need to change my window. First of all, my x minimum needs to go to about 24 here. And my y maximum, my y minimum, let's set the y minimum to about 65. And the y maximum to 73. So let's actually change this real quick. Let's go from 60 to 80 just to keep it simple. Okay, so our graph is going up and down off the screen. Let's change our window just a little bit more. We'll go from about 50 to 90, just so we can see the whole picture of what's going on. Alright, there's our graph, nice and smooth curve. Now, the question that it first asked us was, when does it first initially equal 70 degrees? Well, in order to do that, all we got to do is graph a line at 70 degrees. Y equals 70. So we're looking at this point right here. Now, we can estimate that, but we can also calculate it. We can calculate the intersection of two graphs. So I'm going to do second, calculate. I want an intersection. I need to get pretty close to this point. There we go. And another guess here. So it says at about 8.57 hours. So if we're estimating to the nearest half hour, that's about 8.5. That would be the nearest half hour. So the nearest half hour would be at x equals 8.5. Well, what would the time then be? Or let's say that would be t equals 8.5, I guess. T equals 8.5, so it's at 8:30 a.m. It's about when it'll reach 70 degrees Fahrenheit. Let's see what else we got here. Estimate to the nearest half hour at what time the temperature will reach 77 degrees Fahrenheit. Well, that's not too bad. That's like the same thing. Except now it's not 70, it's 77. We go back to our graph. So it looks like it's going to be at this point right here, maybe 10 or so. I don't know. Let's check it out. Let's find the intersection. Second, calculate the intersection. So we're about there. It looks like it's right at about 10 hours, but let's go ahead and check it out. Second curve. Guess. The intersection is at 10.5, so that'd be at 10.5 hours. So at t equals 10.5, that means it's at 10:30 a.m. These are pretty easy questions. What is the cost per day of cooling the office if the desired temperature is 70 degrees Fahrenheit. Show your reasoning. Okay, so let's see what's going on here. Remember that first, this air conditioning unit is going to turn on whenever it hits 70 degrees because it wants to cool it back down to 70 degrees. And then it's going to stay on no later than 6. So at most it'll go till 6. But it starts right when it hits 70. And when does it hit 70? It hits 70 at 8:30 a.m. So we know that when T equals 8.5, the air conditioning turns on. So that's one time when it starts. Let's see when it turns off. Well, we need to see if it hits 70 degrees again, like it does right here. That means it's definitely going to turn off. But let's see when that point is. So the second intersection. Oh, we need to change this back to 70. You see that we hit it once here, but let's see where else it hits it. So the second intersection, I'm pretty sure that's after 6 p.m., but just to double check. We're going to calculate our second intersection. So I did second and then calc up above the trace button. Now I'm scrolling over. Looks like we're about there. So probably about 22 hours. That's definitely past 6 o'clock. That's more likely 10 o'clock. Okay, in the evening. So it turns on and then it turns off at 6 p.m. which is T equals, what time would that be? That's going to be minus 6 hours from 24, so that's 1800 hours. T equals 18. So we're going from 8.5 to 18. Well then, we need to calculate the cost, and the cost is the integral of c of x from 8.5 to 18. Let's see what that's going to be. First of all, we need to figure out what c of x is. It's this big fancy function here, and look at this. It's t of x minus t of 0. Well, if we want to cool it to 70 degrees Fahrenheit, that means that this is going to be this original function minus t of 0, which is 70. So let's go ahead and put that in. This function down here is going to be t of x, which is the top one, minus t of 0, which is that one. So I'm going to have second vars. Whoops, I didn't want that. I just want vars. Then I'm going to go to y vars function and y1 minus vars y vars function and y2. That means I'm going to have this t of x, which is y1, minus t of 0, which is our initial desired degrees, which is 70 degrees in this case, 70. I'm going to go ahead and turn off the other two functions. And then I'll integrate that first one. So now I'm going to go to my graph. Now even if the graph doesn't appear here, that's fine. I don't really care because I know that I'm just going to do second, calculate the integral, which is number 7. And my lower limit is 8.5. My upper limit is 18. Then it calculates the area. It says $114.15. So our answer then would have been $114.15. It's a lot for one day with one office. let's see what we would have here at 77 degrees. That's very similar. In fact, we only need to change one thing. Well, we need to change a couple things, I guess. We need to change this 77, and then we also need to think about our boundary this time. Our boundary, it turns on at 10:30 a.m. That was at t equals 10.5. And it's off at 6, which is t equals 18. So we have the integral from 10.5 to 6 of c of x. And remember, c of x is really the original temperature function minus the initial value, which in this case is going to be 77. So let's see what that would equal. So we have these two turned off. We're going to integrate just the third one. So we graph it. We go to second, calculate. We're going to integrate. The lower limit this time is 10.5. The upper limit is 18. And the total cost, if we raise it to 77 degrees, is about $55. So we got $54.92. $54.92. That's a pretty big drop in cost just by saying that we'll raise the desired temperature to 77 degrees instead of starting it at 70. That's something to consider, those of you that are going into businesses. All right, next. Number 3, we're going to wrap up the calculator portion here and move on to the non-calculator as well. After that, the problem deals with functions defined by x cubed minus 3bx. So let's go ahead and plug something like that in. So we want to say b equals 1, b equals 2, and b equals 3. So we're going to have 3 different functions here. It's going to be x to the third power minus 3 times, in this case, 1, x. And our window, I don't know if you guys noticed, but it was going from -5 to 5 in the x direction. But in the y direction, it was going from -15 to 15. Ooh, not 115. -15 to 15. So let's see what that graph looks like. That's pretty simple and straightforward. Let's go ahead and multiply this b by something else and see what we get. This one's going to be x cubed, just like the other one, x cubed. And we got minus. Now it's going to be 3 times 2 times x. If we graph that one, because that one's going to rise a little bit higher and go down a little bit higher. It's going to have more exaggerated dips. And then the last one will probably have the same kind of pattern. It's going to exaggerate those dips even more. We'll have x cubed minus 3 times 3 for our b, and then the x. There we go. Alright, so when we're looking at this, I don't know if you guys noticed, but on each of these we pass through 1, what is it? That's not 1, is it? No, it's 3. We pass through 3 on the first one. Then we pass through 6 on the next one. Then we pass through 9 on the one after that. Oh no, that's not what we passed through. Pardon me. Okay, so if we're looking at this, we pass about here on the first one. Come back to 0, and go back up. But then for the next one, it goes a little bit further out. Still comes back to 0, and goes back out again and up. And the last one, it goes even further So this first one, this is for b equals 1. This next one, this is for b equals 2. This last one is for b equals 3. That's part A. I actually could have done it on this page, but I did it on the first page. So let's go ahead and jump to part B. Find the x and y coordinates of the relative maximum of the points of f in terms of b. So x and y coordinates of the relative maximum. Well, that means it's going to be somewhere out over here. We're looking for these maximums. That means if we start with f of x equals x cubed minus 3bx, then we're going to look at the first derivative in order to determine where that flat spot is. We're going to set it equals 0 to find that flat spot. This will give us 3x squared minus 3b. Following simple pattern rules, we can factor out a 3. Then we have x squared minus b. And if we were to factor that even more, this would be 3 times x plus the square root of b times x minus the square root of b. It's a difference of squares. If we set that equal to 0, this 3 isn't really going to change anything, but we find out that x equals either plus or minus square root of b. Well, looking at the graph and having the interpretation that we can apply here, we know that this maximum in each of those is going to be square root of b. Negative square root of b, pardon me. So x is equal to the negative square root of b for the maximum. Y is going to equal to f of square root of b. So I'm going to plug in square root of b into the x values, which means I have b to the 1/2 power. Then I'm going to cube that, minus 3 times b times b to the 1/2 power. You might be wondering, why did I choose to make this b to the 1/2 power? It makes it a little bit easier for doing some of the algebra, combining the terms and multiplying to other powers. So let's see what that would balance out to. We got b to the 3/2 minus 3b to the 3/2. I can actually combine those because it has the same base and the same power. So it's like 1 minus 3. It's going to be negative 2b to the 3/2. That my x and y coordinate for the max is at negative b to the 1/2 and negative 2b to the 3/2. That's my x and y value. That's not too bad. Let's see what we get for part C here. It says find the x and y coordinates of the relative minimum points of f in terms of b. Wow, now that's going to be a little bit different. The only main difference is that if we look at the other side, the x value is equal to the positive square root of b. And y is going to be equal to f of b to the 1/2 or square root of b, which is really b to the 1/2 to the 3rd power minus 3 times b to the 1/2 right here. I just realized I made a mistake. You guys probably actually caught it. Right here, this is negative b to the 1/2. That makes this and this positive. That makes this positive, and that's not a negative 2 anymore because it's 1 plus 3, which makes this 4. That also makes this piece here 4. Which makes a lot more sense because b is a positive number and its y value is positive, therefore that should be a positive coefficient as well. So when I'm looking at this one, I'm already kind of having some intuition as where it's going to be going based on the calculations we did in the last one. We're going to get b to the 3/2 for that first term. It's going to be minus 3b to the 3/2. So just like before, we can combine like terms, so this time we do get negative 2b to the 3 halves. Well, that's our y value. So the min is at x equals b to the 1 half, and y equals negative 2b to the 3 halves. There we go. Part D. Part D here, it says show that for all values b greater than 0, the relative maximum and relative minimum points lie on a function y equals ax cubed by finding the value of a. So it's saying that those 2 points are still going to be here. Oh, I see what they're saying. Let's go back to this. What they're asking, they're saying that those 3 points there are going to line up, and then if we line up the mins over on this side, so we're going to have a function here in which these points are all connected. Wow, that's an interesting thing to do. Sorry about that for a second to answer a quick phone call. But anyways, we're back here. So we're trying to find the value of A in part D, and you're asking yourself, if I need to solve for a variable, in this case A, then I need the other values, which are x and y. Wait a second, we know x and y no matter what the max and min values are. So I know that y, let's say for the maximum value, y is going to equal, let's see what we got here. For the minimum value, let's go do the minimum value. We got b to the 1 half for x and negative 2b to the 3 halves for y. So this is going to be negative a times our x, and y is over here. This is going to be b to the 1 half. Then on this side we have, and that's cubed. And then on the other side we have negative 2b to the 3 halves. Negative 2b to the 3 halves. Well, if I were to simplify this, I would get negative 2 times b to the 3 halves equals negative a times b to the 3 halves. Hey, that's kind of interesting. That means that negative 2 equals negative a, therefore a equals 2. Let's see if I get the same thing going the other way using the maximum values, just to confirm. That means I'd have negative b to the 1 half and 4b to the 3 halves. So I'd have 4b to the 3 halves is equal to negative a times negative b to the 1 half cubed. If I multiply this out, that means I have 4b to the 3 halves equals positive a times b to the 3 halves. And in this case, when I divide by b to the 3 halves, I get that 4 equals a. Is that the same as what we got over here? Let's double check. Well, let's go ahead and graph that and see if that works for us. that means that we would have y equals a new function. This is the best way to check any type of answer. It's going to be -2 times x cubed. Let's see what we forgot to write in here. Oh, I put minus, but it should be a negative. There we go. So there's our first graph, there's our second graph, here's our third graph. And I think that's the winner right there. Looks like this runs right through the mins and maxes. That's pretty cool. Pretty cool way of looking at those two graphs and how they're related. So the second one, I might be missing something, but this for sure, our answer A would be equal to. We're going to continue the non-calculator in the next video.